So today we're having a look at section 11.6, which is surfaces in space. For the moment we've discussed one surface, which is planes, and today we are expanding that notion to three other types of surfaces, which you can see here: cylindrical surfaces, quadric surfaces, and something you remember from AP Calculus, surfaces of revolution. So for the first one, a cylinder is a little bit more in the context of multivariable calculus than what you just have in your mind when you think of a cylinder. A cylinder is actually any shape like the one represented here. So how do we define that? We let C be a curve in one of the coordinate planes. In this example, this is in the xy plane, so this is the curve C. And then the cylinder is the surface that is generated if you draw lines perpendicular to that plane, so vertical lines in this case, and like basically cover or loop around the curve. That creates a cylinder. So don't be fooled, this is not a full inside, even though this color seems different. It's a surface, it's not a solid. So you also have cylinders that where the curve is in the YZ plane or in the XZ plane. And in fact, we're going to see a few examples right now. Firstly, sketch the following cylinder: z equals x squared. So you realize that actually y doesn't make an appearance here. So you can think about that as a 2D curve, z equals x squared. We're going to sketch the parabola ignoring the y-axis. So it's a little bit of an effort. This is the x-axis, this is the z-axis, and we want to sketch the parabola in the xz plane. If we wanted to sketch z equals x, be aware that the line z equals x would be coming this way, which is a little counterintuitive when you think of y equals x. The reason is that x is pointing in that direction. So once we've sketched z equals x squared in the xz plane, we realize that y doesn't matter. We can pick y equals 0, or we could pick y equals 1, y equals 2, y equals 3. We would always have exactly the same parabola, and therefore the cylinder is actually a parabolic plane, if I can say, that goes in this direction. Secondly, y equals sine z. So here x is missing, and in fact that's going to be characteristic of cylinders, is that one of the three variables is missing. So we want to sketch that for z bounded by 0 and 2 pi. So once again, y equals sine z. This is a 2D curve in the yz plane. You just have to be careful. What is the wavy shape going to look like? Where is it going to go up and down, if I may say? So y and z, if you were able to, or if you're able in your mind to think of yourself as being behind the plane and then y turning it up, you may recognize, oh, y equals sine z goes like this. And therefore, because x can be any value, this curve will be able to move along the x-axis, and it forms a trigonometric cylinder, if I can say, just like this was a parabolic cylinder. And we stopped at 0 and 2 pi. If there wasn't this limit, of course, it would just keep on going. The second group is quadric surfaces. You might recognize these surfaces, some of them at least, and they are all tied together by one long algebraic equality, which is written here: ax squared plus by squared plus cz squared plus j equals 0. Whatever value you plug in for a, b, c, d, e, f, g, h, or e, h, g, you will get one of those depending on some conditions. Now, in this course, we will only focus on surfaces such that D and E and F are all equal to 0. What does that mean? This is actually the entire thing, is the combination of all degree 2 polynomial. So we have x squared degree 2, y squared is degree 2, z squared is degree 2, xy is degree 2, x is degree 1 times y degree 1, xz is degree 2, yz is degree 2, and then those that are smaller than 2, x, y, z, and constant. So degree 1 and here degree 0. So what we'll do in this course, and this is very typical, we just ignore all those that combine two of the variables. So we will have x squares, we will have y squares, we will have z squares, we will have x's, y's, and z's, and we will have constants, but not the combinations. This is not unusual. Let me just show you the similar situation in 2 dimensions. If I look at, so this is the same but without z's. So we have ax squared, we have by squared, we have the combo xy, and then we have x and y and constants. All you can do with these a, b, c, d, f, and g are the conic sections. So in this example here I have an ellipse. If I change b to -1, it gives a hyperbola. Now notice that c equals 0. The c is the combined terms of x and y. If I change this to 2, for example, the effect doesn't change the type of graphs I may obtain, but it changes the angle. And if we change, so here the hyperbola is slanted. If I change this back to 1 or maybe to 4, we would have an ellipse and it's slanted. So likewise, when we select D, E, and F equals 0 here, we are not removing any of the options of surfaces that might appear. What won't happen is that the cones will always be vertical or horizontal. The ellipses will always have their axes lined up with the x-axis, y-axis, z-axis, and so on and so on. If you start playing with D, E, F, then your elliptic paraboloids and so on will start to tilt in some directions. There's a few prototypes that are worth being vaguely aware of. You could also decide, I'm just going to memorize all these, it's going to make my life easier, but it's not necessary. They are, first of all, if you only have x squared, y squared, and z squared, so it has to be equal to a positive number, then it's a sphere. X squared plus y squared plus z squared is the prototype of a sphere. If you switch one of these and you decide that a is not 1, so for example 4x squared plus y squared plus z squared equals 1, then you get an ellipsoid. The second type that is a prototype of surface is when you have x squared plus y squared minus z squared. So it's represented down here. And then there are 3 options. It can be equal to a negative number, it can be equal to 0, or it can be equal to a positive number. And that switches from hyperboloid of 2 sheets right here to a cone right here if it's equal to 0, to a hyperboloid of 1 sheet if it's equal to a positive number. So it kind of transitions from these 2 sheets, just reaching to each other and touching each other here, and then widening from the center. Finally, we have paraboloids. If it's x squared plus y squared equals plus or minus z, then you have, so think about this as z equals x squared plus y squared. It's actually 2 parabolas in each direction, so we would have an elliptic paraboloid. If it's x squared minus y squared equals z, and it's a little more subtle, it gives this shape here, which in the x direction is an upward parabola, and in the y direction, we can see here, is a downward parabola. That's how you make a saddle shape. All right, and if we go back to the one before last, the paraboloid will open up or open down depending on if it's z equals or negative z equals. You can also phrase that as z equals x squared plus y squared, or z equals minus x squared minus y squared. So there's an example below where we could have a look here and recognize the prototype as being the third group here, x squared plus y squared minus z squared equals 1, so the answer would be a hyperboloid of 1 sheet. But let's just forget that for a moment, because more often than not, we won't be able to find or see a prototype. So we want to be able to deal with equations like that calmly. There's no recipe, there's no miracle system, but you just look at it and make some choices. For me, the best choice is to first look at the axis intercept. So I would be curious, without knowing anything about the surface, to look where does it intersect with the x-axis. And to do that, you set up y equals 0, z equals 0. And that gives you x equals plus or minus 1, right? X equals plus or minus 1. So x equals 1 is here, x equals negative 1 would be over there. What about intersections with the y-axis? This time x equals 0 and z equals 0, and it again gives us 2 points. Is that enough to sketch the surface? Certainly not. It may give us no idea, but I think this is a good way to start. What about z-intercepts? Well, if I set up x equals 0 and y equals 0, I get z squared equals negative 1, which is impossible, so that translates as there are no z-intercepts. So that's really interesting. That might lead you to wonder, well, there's never any z-intercept. I'm going to be curious about knowing what shape this surface is if I only look at the xy plane. So just picking z equals 0, I would sort of forget everything that's above and everything that's below and just look at what this kind of section of the surface looks like in the xy plane. So by setting up z equals 0, we see that this term disappears. We just get x squared plus y squared equals 1, which is a circle. That makes complete sense now with the intersection that we found earlier. We could have started with just that, setting up z equals 0, but who would have known it would be so clear? So now we know that whatever the surface is, it is a circle if I only look at its trace in the xy plane. And that leads me to wonder, well, what about if I choose z equals 1? What happens if I choose z equals 2? What happens if I choose z equals 3? And what you may realize is that if z equals 1, it's going to be x squared plus y squared equals 2. If z equals 2, it's going to give me x squared plus y squared equals 5. If z equals 3, it's going to yield x squared plus y squared equals 10. And all of these are circles with expanding radii. What about negative numbers? It gives exactly the same. If z equals negative 3, it's still going to be a circle, x squared plus y squared equals 10. So what I'm doing here is I'm seeing different level curves at heights z equals 1, z equals 2, z equals 3, and also negative values of z. So I can start sketching circles at the height z equals 1, a larger circle at z equals 2, which the radius you can easily find by looking here, and same for negative values of z. And that, when I do that, will help me realize that the surface is going to be a hyperboloid of one sheet, like it's represented here. We could have also tried to sketch the surface in the xz plane or in the yz plane and look what happens in those situations. And if you do that, great. If you get to a dead end where you don't get a feel about what the graph looks like, then just start a new strategy. It happens that in this example that I'm talking about right now, the circle was really the best strategy to help us. But doing this exercise for the first time, out of the blue, I don't know if I would have started with that for sure. So last group is surfaces of revolution. Now we remember what a surface of revolution is from AP Calculus. This is an example here where it's rotating about the y-axis. So what do these equations look like? It's really interesting, but this is the general formula. X squared plus y squared equals a certain function of z. X squared plus y plus z squared equals a certain function of y. Y squared plus z squared equals a certain function of x. And if it's a function of z, then that means the function is rotated about the z-axis. If it's a function of y, it's rotated about the y-axis. If it's a function of x, it's rotated about the x-axis. I said it's a function of z you can see that it's a bit more, it's actually a function squared. And this function is not any function, it's actually going to exactly correspond to the radius of the circle at that value of z. Why are these equations like that? Well, let's start thinking only, we're going to look at an example where we rotate about the z-axis, and we're going to first ignore the y-axis entirely. And we're going to think I have a curve in the xz plane here, which is x equal something of z. X equals a function of z. So I sketched it in purple here. You should try to think in your head that this is in the wall that's here, in the xz plane. Now, if I choose a certain height z, it's written in green here, and I plug in this input z in the function, it yields x, right? It yields this length there, which would allow me to find the point in the xz plane. Now, what I want to have a surface of revolution is I want that x is not just the input, is not the only input. I don't want this to be the only point f of z. I want any point that's a combination of x and y along a circle to also be solutions to f of z. And this is why, instead of only having x equals f of z, I want to set it up as x squared plus y squared equals that value, the radius, squared. So it's really quite clever. And the same happens if we want to rotate about the x-axis or the y-axis. We first need to find an expression for the radius, and then we can just add this kind of circle thing. This creates a circle from what was originally just a point in the plane. So let's see an example that's going to help. Find an equation for the surface formed by revolving the graph of 9x squared equals y cubed about the y-axis. So firstly, let's recognize that this in the xy plane is a certain curve, 9x squared equals y cubed. And this curve, if you do it on your calculator, you would see that it has this shape. So this is 9x squared equals y cubed in the xy plane. So we're talking about a curve in a 2D space. Now, I want this to represent my radius. So I would like to find exactly, this is the radius somewhat, I would like to find what this is in terms of y. So I would like to write it as x equals something. It's easy, x equals plus or minus the square root of y cubed over 9. I only care about the positive actually, because since I'm going to rotate this, it's going to include the negative part when I go behind the y-axis. So let's just say this is x equals positive square root of y cubed over 9. This y cubed over 9, which is in very light yellow here, is the radius of my circle. It's kind of, this salami slice has a radius of root y cubed over 9. So just to create the surface of revolution, I want x squared plus z squared, which is a circle parallel to the xz plane, to be equal to that radius squared. And that's what I do. So I plug in this squared. It happens that the square root and the square cancel out, and here's my surface of revolution. So this last type of functions of surfaces of revolution, it's a little hard to wrap our heads around this concept, but practice will certainly help. And that is all for section 11.6. Thanks so much.